For the very first time in human history, a telescope pointed at another star and actually saw a planet with its own eyes, not a shadow, not a flicker of dimming light, not a mathematical inference buried inside a graph. An actual image, real light captured from a real world orbiting a real star over 100 light years away. The James Webb Space Telescope just achieved something astronomers have been chasing for decades, and the story behind how they pulled it off is almost as fascinating as the discovery itself. Stick around, because this isn't a simulation and it isn't an artist's impression. This is a genuine photograph of another world, and by the end of this video, you'll understand exactly why scientists are calling it a turning point for how we search for planets beyond our own solar system. Let's start with a problem that has haunted planet hunters since the very beginning of exoplanet science. Finding planets around other stars is almost absurdly difficult, and the reason comes down to one brutal fact of physics. Stars are blindingly, overwhelmingly bright, and the planets orbiting them are, by comparison, incredibly faint. Trying to directly see a planet next to its star is a little like trying to spot a firefly hovering directly beside a lighthouse beam from miles away. The lighthouse simply drowns out everything nearby. Because of that challenge, almost every one of the nearly 6,000 exoplanets discovered so far has been found using indirect methods. Astronomers watch for a planet passing directly in front of its star, causing a tiny, measurable dip in brightness. Or they detect the subtle gravitational wobble a planet causes as it tugs on its host star while orbiting around it. These methods work brilliantly. They've given us an incredible catalog of distant worlds, but they all share one limitation. Nobody actually sees the planet itself. They see its effects, its fingerprints, left behind on the light of its star. If you're new to this channel, we cover discoveries exactly like this one every single week. Real breakthroughs happening in real time. So make sure you're subscribed before we continue, because this story is a genuine milestone in the search for other worlds. Direct imaging, actually capturing a picture of the planet itself, has always been the gold standard, and also the hardest method by far. It requires blocking out the overwhelming glare of a host star with extreme precision, while still preserving enough sensitivity to detect a planet that might be 1,000,000 times fainter. For years, only the largest, hottest, and most distant planets, sitting far enough from their stars to be somewhat separated from that overwhelming glare, were even theoretically within reach of this technique. In June of 2025, a team of astronomers led by a researcher at the French National Center for Scientific Research announced they had finally pulled it off in a genuinely new way, using Webb's mid-infrared instrument known as MIRI, equipped with a specialized coronagraph designed specifically to block out starlight. The team turned their attention toward a young star called TWA-7, located roughly 111 light-years from Earth, in the southern constellation Antlia. TWA-7 isn't just any star, it's a young star, still surrounded by a swirling disk of leftover gas and dust, the exact kind of raw material planets are born from. Astronomers had already mapped out this disk in impressive detail, noticing it was structured into distinct rings, similar in some ways to the rings of Saturn, but on a scale spanning an entire planetary system. That kind of structured, ringed disk often hints that something inside it, likely a planet, is gravitationally sculpting the material into those distinct bands. Using MIRI's coronagraph to suppress the otherwise blinding light of the star itself, the research team carefully processed the remaining image, searching for any faint source of infrared light hiding within that debris disk. And there it was, a small, faint glow sitting precisely within a gap in the rings, exactly where a planet's gravity would be expected to carve out that kind of space if it existed there. If discoveries like this one, genuine photographs of planets orbiting distant stars, are the kind of thing that gets you as excited as they get me, do me a quick favor and hit that like button. It genuinely helps this channel keep making videos exactly like this one. The object was named TWA-7b, and what makes it so remarkable goes far beyond simply being Webb's first direct planet discovery. Based on its brightness and the physics of how young planets cool and radiate heat over time, researchers estimate its mass at somewhere around 100 times that of Earth, roughly comparable to Saturn. That might not sound small at first, but in the world of direct imaging, it represents something genuinely historic. TWA-7b is the lightest planet ever captured using this technique, breaking past a barrier that had limited direct imaging almost exclusively to massive gas giants many times heavier than Jupiter. One of the lead researchers described the core challenge in refreshingly simple terms. The problem, she explained, is that the star is bright and the planet is very faint. That single sentence captures decades of frustration for planet hunters working with this method. Every previous attempt at direct imaging had to compromise, either by targeting only the largest, brightest planets, or by accepting extremely limited detail in the resulting images. Webb's extraordinary sensitivity, combined with the specialized coronagraph technology developed specifically for this project, finally pushed that boundary further than ever before. This discovery matters for reasons that go well beyond a single interesting picture. For decades, the ultimate long-term goal of exoplanet science has been directly imaging smaller, cooler, more Earth-like worlds, planets that might actually be capable of supporting life. Every planet discovered through indirect methods gives scientists useful data, but nothing compares to actually capturing an image and eventually a full spectrum of light directly from the planet itself, revealing details about its atmosphere, its composition, and potentially even signs of habitability. TWA-7b, at roughly the mass of Saturn, is still far larger than Earth, but its discovery proves that Webb's imaging capabilities can now reach smaller, fainter worlds than anyone had previously managed to capture directly. Researchers involved in the project were candid about what this really represents. One young researcher who worked on analyzing the data put it with genuine enthusiasm, saying this feels like just the beginning, and that many more direct images of exoplanets are coming, images that will reshape our understanding of their physics, their chemistry, and how they actually form. There's also something poetic about where this planet was found. TWA-7 is an extremely young star system, meaning astronomers are essentially watching a planetary system caught in the middle of its own formation. The same violent, chaotic process that once shaped our own solar system billions of years ago. TWA-7b, sitting neatly inside a gap in the star's debris disk, offers direct, visual evidence supporting a theory astronomers have held for years, that planets actively carve out these gaps as they form and grow, sweeping up material and gravitationally reshaping the disk around them. Scientists have long inferred this kind of planetary disk sculpting indirectly, using models and simulations built entirely on physics and mathematics. Now, for the first time, there's an actual direct image showing a planet sitting exactly where those models predicted a planet should be, carving out a gap precisely the way theory said it should. That alignment between prediction and direct observation is exactly the kind of confirmation that pushes an entire scientific field forward with confidence. Researchers have stressed that this finding, while extraordinarily promising, still requires additional confirmation through follow-up observations before it can be considered fully verified beyond any doubt. Faint infrared sources near bright stars can sometimes be mimicked by background objects or unusual dust structures, and rigorous science demands ruling out every alternative explanation before declaring victory completely. But the evidence gathered so far, the object's position precisely within a gap in the disk, its brightness, matching exactly what a young Saturn-mass planet should look like, and its consistency across multiple observations, has left the research team confident they've genuinely captured Webb's first true direct image of an exoplanet. This achievement builds directly on Webb's very first exoplanet image, captured back in 2022, showing a much larger, much hotter gas giant called HIP 65426b, roughly 6 to 12 times the mass of Jupiter, sitting 385 light-years away. That image proved Webb's direct imaging capability worked at all. TWA-7b proves something far more significant, that the technology has advanced enough to start reaching genuinely smaller, fainter, more Earth-comparable worlds, exactly the direction the entire field has been racing toward for years. Looking ahead, scientists see this discovery as a genuine proof of concept for an entire new era of direct exoplanet imaging. Every improvement in coronagraph technology, every refinement in image processing techniques, brings researchers one step closer to eventually capturing direct images of rocky, temperate planets orbiting nearby stars, the kind of worlds where liquid water and potentially life could genuinely exist. WA-7b won't be that planet. It's a young Saturn-mass gas giant, still glowing faintly, with leftover heat from its own formation. But it represents proof that the technology needed to eventually find and directly photograph something far more Earth-like is not just theoretical anymore. It's actively working, right now, on real distant starlight. It's worth taking a moment to appreciate exactly how much engineering went into making this coronagraph work as precisely as it did. Blocking starlight sounds simple in theory, just place something in front of the bright source. But in practice, it's one of the most delicate challenges in modern astronomical instrumentation. Even the faintest scattered light leaking around the edges of a coronagraph can completely wash out a planet 1,000,000 times dimmer than its star. The specialized coronagraph used for this observation was specifically designed and built to suppress that scattered light with extraordinary precision, developed through years of careful engineering by teams working specifically on this exact problem. Without that level of precision, TWA-7b would have simply remained invisible, buried completely within the glare of its own star, exactly like every other faint planet that direct imaging has struggled to capture for decades. There's also a fascinating layer of image processing behind this discovery that rarely gets mentioned outside of technical research: papers. Even after the coronagraph did its job suppressing most of the starlight, a faint residual glare still remained in the raw data, enough to potentially hide a planet as faint as TWA7b. Researchers had to apply advanced computational techniques to further subtract that remaining light, essentially digitally erasing the star's leftover glow pixel by pixel, until only the faint infrared source belonging to the planet itself remained clearly visible. That combination, cutting-edge hardware paired with sophisticated software processing, is exactly what allowed a planet this faint to finally become visible after decades of remaining just out of reach. This kind of layered achievement, hardware and software working together at the very edge of what's technically possible, is becoming something of a signature for Webb's most groundbreaking discoveries. It's rarely a single breakthrough moment. It's usually the culmination of small, incremental improvements across multiple systems, all coming together at exactly the right time to finally cross a threshold that previous instruments simply couldn't reach. WA7b is a perfect example of that pattern, a discovery made possible not by one single innovation, but by an entire chain of careful engineering decisions finally paying off together. Scientists involved in this research have already begun planning follow-up observations, hoping to eventually capture a spectrum of light directly from TWA7b itself, rather than just an image. A spectrum would allow researchers to study the actual chemical composition of the planet's atmosphere, revealing details about its temperature, its clouds, and the physical processes shaping this young world as it continues cooling down from its own formation. That kind of detailed atmospheric study represents the true next frontier for direct imaging, moving beyond simply confirming a planet exists, toward genuinely understanding what it's actually like. There's a broader significance here too, one that connects directly back to why astronomers care so deeply about young systems like TWA7 in the first place. Watching a planetary system in its early formative years gives scientists a rare kind of natural laboratory, a chance to observe the physical processes that once shaped our own solar system billions of years ago, back when Earth itself was still forming out of leftover debris surrounding our own young sun. Every detail captured from TWA7b, its position within the disk, its estimated mass, the gap it appears to have carved into the surrounding rings, adds another data point to scientists' understanding of exactly how planets like Jupiter and Saturn, and potentially planets like Earth, actually come together out of nothing more than swirling dust and gas. That's part of what makes this particular discovery resonate beyond just the astronomy community. It isn't only a technical milestone in imaging technology, it's a genuine window into the earliest chapters of how planetary systems, including systems that might one day host life, actually begin. If Webb just captured its first direct image of a planet roughly the mass of Saturn, sitting over 100 light-years away, what does that tell you about how close we might actually be to someday capturing a real direct image of a genuinely Earth-like world orbiting a distant star? Drop your thoughts in the comments and let me know whether you think we'll see a direct image of a truly Earth-like exoplanet within our lifetime. If this story pulled you in the way it pulled me in while researching it, hit that like button. It genuinely helps this channel. Keep telling stories like this one, and subscribe if you haven't already, because Webb's direct imaging program is only getting started, and when the next breakthrough comes in, we'll be covering it right here. 111 light-years away, inside a ring of dust still shaping itself into a solar system, a young world sits glowing faintly in infrared light, the very first planet Webb ever truly saw with its own eyes.